Okay, let's do our first lesson of the year. We will be looking at some review stuff. So you'll probably need some calculators. You want to get those out. And we're going to shake the cobwebs off of our brains today and get us back into chemistry. Okay, so I'll start as soon as I find my arrow. I don't want to use that one, but I will. Okay, so looking at this nice little instrument that holds liquids and measures them, what is this called? A graduated cylinder. We have a series of liquids that they're not dissolving with each other because they're very defined. What is that type of mixture called when you can see clear separation between phases? What, Naira? Heterogeneous mixture, correct. Not a homogeneous or homogeneous mixture. So that's something to be thinking about as we go through this problem. We have to identify liquid 1 and 2. That's the goal of this. We know we have water and we have mercury, and they give us all these densities. Another thing I want you to pay attention to is the fact that we're at 25 degrees Celsius. What does it mean to be at 25 degrees Celsius? What does that mean to us as human beings? Standard temperature, what does that mean? Roomish, room temperature. Okay, it's a little cooler than what we're experiencing right now in Texas because our air conditions don't work that great. But this is considered room temp. So that's going to be an important fact when we're figuring these things out too. So let's start with liquid number 3. Liquid number 3, what has to be true about its density? I heard it, higher than water but lower than mercury, right? Because the heaviest falls to the bottom. That's why mercury is down low, because it's got the highest density. So what are some options that liquid 3 could be? I'm sorry? Dichloromethane, aluminum, or bromine. Oh my goodness, how are we going to find out which it is? Which one do we know it just can't be? Why not? Because aluminum is a solid at room temperature, right? Do we all agree with that? Okay, I'm glad. I'm glad y'all aren't questioning that. That's good. Okay, so we know it can't be aluminum. Now, we have to pick between dichloromethane and bromine. No, dichloromethane is, with the chlorines on it, it's liquid. It's a polar molecule, so it's going to be attracted to each other, so it's going to be liquid. And we know bromine is a liquid as well at room temperature, because see on the periodic table how it's blue? Okay, those are liquid at room temperature. So both of those are liquids, so that's not the issue. Any other ideas? They give you some more information there next to the words. What else could it be? Okay, yes. Good, yes, it has to do with polarity. What about the polarity? Let's talk about the polarity of these things. What's water? Polar. And what's mercury? Mercury is just a single thing with very weak intermolecular forces. Okay, so it's going to, what do you think? Yeah, we need a nonpolar. And I don't really even care what mercury is. This is going to be an issue. This has to be nonpolar. Why? Exactly. If this were not nonpolar, if it were polar, it would mix with the water, and we would not get a separation. So what is, mine is horribly messy. What is liquid number 3 then? It's got to be bromine. Otherwise, it would mix with the water. Okay? So now you have all the tools to tell me what liquid number 1 is and why. What are 2 options for liquid number 1? Hexane and ethyl alcohol are my options. So which one is it? Hexane, and we know that because it's nonpolar and it will not dissolve. We call it miscible. Nonpolar stuff doesn't dissolve. It's not miscible with polar stuff. Okay? All right. So hopefully that got some cobwebs out of your head a little bit. So now we're going to go through math really fast. We're going to do what you did within a week in Chem 1 in a very short period of time. So, differences between precision and accuracy. Does anybody remember?
So precision is when you have a lot, like when maybe you don't hit the target, but like all the shots are right next to each other.
Precisions are when all the shots are next to each other. Can we put that, that's correct. Can we put that in a, like define it, that would work for any, Jacob? Consistency, another word I'm looking for, I'm trying to draw repetition, repeatability, okay? So if I were to step on a scale and it says I'm 98 pounds and I get off and I step on it again, it says 98 pounds, and I keep stepping on it, it says 98 pounds, that's a precise instrument because we get repeated results. But is it accurate? No. You don't hurt my feelings. I know I'm not 98 pounds. Giving blood has never been a problem for me. Always been within the right range for that. Probably since I was 3, but that's okay. So looking at this, we can now decide that things that are repeatable are precise. And what does it mean to be accurate then? Correct. Kate said close to the actual value, and that is what it is. So knowing that, let's look at which sets of measurements are precise. Which are precise? B and C. Which are accurate? Yeah, pretty much just C. Now, we could get into a conversation about, let's pretend these were actual numerical values. Say that was 5 trials in an experiment and you had 5 different numbers. What do you usually do with your different trials in a mathematical experiments? You usually average them. So we don't know. Maybe this is accurate after we average them. In the world of darts, it's not. In the world of darts, this is not accurate. But this potentially could be accurate in our chemistry world because that might average to right there. But who knows? We don't know. So we're going to just say that the only thing that was accurate was C, and which are both C. Okay? All right. Explain the difference between an exact and inexact number. Does anybody remember? Naira? Exactly. Exactly. Get it? Yeah. An exact number is a counting number. Okay? And an inexact number is something that you're going to measure. So exact is a counting number. Inexact is something you measure. So right now, including myself, we have 30 people in this room. So that is what kind of number? It's an exact number. It's a counting number. How many sigfigs is associated with that? Infinite number of sigfigs. Last class there was 28, and they're like 2, and I stumped them. I didn't stump y'all, but it's an infinite number of sigfigs. Meaning, does it mean anything different for me to say to you, there's 30 people in here, or there's 30.0 people in here, or there's 30.00 people in here? That has no difference in meaning. So there's an unlimited number of sigfigs with counting numbers, okay? However, if I said that's 30 grams, or I said that's 30.0 grams, or I said that's 30.00 grams, those are very different because it talks about the capability of that instrument, how accurate. The more and more decimal places on that number, the more accurate the value. So there is a difference between that. Y'all get that? Okay. So, in each case, exact or inexact, number of faces, mass of 6 apples, number of apple seeds. Okay, now this is something we kind of have to pay attention to. We are not going to jump from the American system to the metric system on a regular basis. We're only doing it today for practice. I don't want you to freak out in tonight's homework about sigfigs on these crazy dimensional analysis that have furlongs and feet and all this American jargon and all this stuff, because we don't do that. Our measurements usually stay within the metric system. So today it's just practicing dimensional analysis and practicing with inexact and exact numbers. So if you look at the metric system, when we say there's 1 meter, to 100 centimeters, that's an exact translation, right? So that's an unlimited number of sigfigs. So what that means is we don't use that when we're determining the sig fig of the overall problem, that conversion. We just look at the given number, okay? Now in this one, theoretically, if we were to have this conversion, we would use the sig figs because this is going from liters to quarts, which is from what system? Liters is a metric, quarts is American. So with that being said, number of feet in 1 mile. Exact or inexact? Exact, because it's within the same system. Systems are defined. When they're defined, that's how they're built, so that's exact. Versus number of liters in 5 quarts, it's inexact, because that's jumping from the American system to the metric system. Or the other way, from the metric to the American system. Okay? All right, sig figs. What? Loving the sig figs. We'll go over the rules really quick because I think you still probably remember these. All non-zero numbers are significant. So if it's a number other than 0, it's a significant digit. Sandwich zeros are significant. So if you have 207, we know that that is 3 sig figs because that 0 counts, right? Leading zeros are never significant. By leading, I mean this. Okay, all of these are not significant. Okay. Does anyone remember what this is called? Dead baby. Did I talk about that in pre-AP to y'all? Yeah. Okay. I'm just going to refresh your memory if you don't remember dead babies. Yeah, is that technically wrong? No. But I'm just telling you from my experience as an AP grader, that could cause problems because sometimes you don't make the dot very dark, and we don't know if that's 5 or 0.5. And that could matter because if you have something like this going on, and it's 0.5 versus 500, and it happens to be meters that you should have converted to kilometers or something, like it could cause some gray area. So I always want you to include the 0. And why we call that dead babies is because there's a tendency, especially in neonatal units in hospitals, for misdosage to occur because of that. So if a baby was supposed to get 0.5 milligrams of some drug, and the doctor with the bad handwriting wrote it like this, and then the dumb pharmacist who didn't pay attention went ahead and gave 5 milligrams, that could potentially kill a child because they're babies, they're tiny. That's a huge difference in drugs. So that's been known to happen. And you can look it up. Dennis Quaid even sued a hospital over the potential, this hospital almost killed his kid with some heparin-based drug that was something going on with him. So anyway, the reason we call it that is because we don't want you to kill babies. And if you're going to come from Westlake and you're going to be a doctor and you're going to work with babies, you'll never kill the babies. So no dead babies. Okay, so determine the number of sig figs in the following quantities. I forgot trailing. Trailing zeros. So if we have 27,000, these are not significant, meaning if I'm at the Spurs game and they say, the announcer's like, there's 27,000 people present today. Do you think there's 27,000 people present? The only significant is we're somewhere in that range, right? We could have 1, who knows? Who knows how many people are here? But that the 27,000, the 27 is what we know for sure. Okay? All right. So let's go through. 3.82. 3 sig figs. 24. 0.0619. 2.1 times 10 to the 4th. 2. What are all these zeros right here? Those are trailing zeros. That's why they're not significant. So when you have anything in scientific notation, you just take to the left of the x. If it's appropriate scientific notation, a number between 1 and 9 with a point and an exponent, then you can do that. Kilometers here, how many? 5. All right, 712,000. 3, good. Okay, now let's talk about using devices. Yes? Oh, I didn't. I underlined the trailing. My bad. Yeah, I didn't cross out exact numbers. This is a correct statement. I was underlining trailing zeros. Okay. devices, using measuring devices. This is a graduated cylinder again, and it's really, really important for you to be able to understand in any measurement you take, you read what you can, and then you add an extra digit. That extra digit is always an uncertain digit, and you have to have that because an instrument should always read the same number of sigfigs no matter what the reading is. So let's take a look at this graduated cylinder. This is called a graduated cylinder. What measurement, let's look at it. Where is it falling-ish? Yeah. Go ahead. On your paper you can't see it? Okay, well, you can, I mean, within, what is it? I mean, you can kind of see. Yeah. To me, it looks like it's pretty much dead on the 43. So it's 43, right? But we can't leave it this because think about what this instrument can do. Do you think we could somehow get the liquid in between two lines? Since we're capable of that, we need to have a digit that could represent that, okay? So we have to guess another digit. So since we're pretty much dead on, what would that other digit be? 0.0, okay? 90% of you would probably have just written 43 and moved on with your life, but you can't because had that line moved, you could read it to that decimal place. So this is the accuracy of that instrument, that 0.1, plus or minus 0.1 is what we would say, okay? So you have to read all the readings out to that. And how many sigfigs is 43.0? 3, okay? So let's practice this a little more with these arrows. These are a little bit clearer, I think. We have a centimeter here. And what do we know for sure about this measurement? It's point what? It's 0.7. What do you think the next one is? And again, the next one's uncertain. It's a guess. I expect you just to guess. It's not, there's no right or wrong answer if you're realistic about it. So what would you want to guess? No. We're not carrying only one uncertain digit. We only add one uncertain digit. And what would that uncertain digit, what could it be? You want to do 0? Cool. You want to do 1? Cool. I heard someone say something 1.5 or something. No. You don't know that. There's no way you would know if it's 1.5. There's no way you could measure that because there's no additional lines in there, right? So the furthest out you can go is guessing this guy right here. Okay? All right, let's look at B. What do we know for sure? 1.5. Sure, 1, 2. I would probably go with like 2 or 3 there, but again, it's fine. You don't have to know that exactly. That's the point. It's a guess. That last digit is a guess digit. And then let's look at the last one. What do we know for sure? 2.8 for sure, and what do you want to guess here? I heard 8 first. That's fine. 8, 6, 9. All that's fine. Okay? So how many sigfigs are, this one had 2, and all of these were 3. So we at minimum, anything beyond the 1, we would expect to have to be 3 sigfigs. This is to the 100th, so this would be a plus or minus 0.01 accuracy. So which instrument is more precise? I mean, more accurate. The graduated cylinder, this was plus or minus what? 0.1. So this one is not as accurate as the ruler. And so where this comes into play in the real world, most of our balances in AP are going to have 3 decimal places. And you're going to go back there and you're going to sit there for an hour and you're going to be staring at this balance at that last digit. It's just floating. It's just jumping. You're like, it's not still. I don't know what it is. That's our guessed digit. So just pick the one that shows up most often. Okay? It's supposed to be uncertain. All right? Okay. All right, calculations with sigfigs. I'm sure you all remember these really quick. There's a difference between when you do multiplication and division versus when you do addition and subtraction, the difference is based on what you round to. In multiplication and division, you round to the number that is the least number of sig figs. So here, this is a 3 sig fig number. This is a 5 sig fig number. So we round to 3 sig figs. So this is what you get out of the calculator. We're going to round it to 3. So that's in all multiplication and division. In addition and subtraction, you round to the least number of decimal places. So here we have a number with 2 decimal places. Here we have a number with none. So our final answer should have no decimal places. When you get this out of your calculator, you just take off the decimal places. Okay? So to see it in action, we have these problems. You don't need a calculator here because they're already done for you. This is all multiplication and division. So since it's multiplication and division, you're going to count sig figs and round to the least. So how many does this one have? 4, then 4, then 3, then 5. So how many are we going to round to? 3. So what would the final answer be? Good. Didn't get you. You got to round it first, and then we have that extra decimal point to get it to 3 sig figs. And they're working on the roof, so y'all missed out. It flooded in here last week. There were many of our classrooms that were not usable. It was bad. Pretty much all new ceiling tiles. It was horrible. Okay, so looking at this, what do we round to? 3 what? 3 sig figs. So what would our answer be? And here's the thing that's really important. 26,500 is correct. I know a lot of you might have said 265 because that's 3 sig figs. Can't do that. That doesn't make sense though, right? Because this number is around 26,500. You can't change the magnitude of the number, okay? So just watch for that. And so here are addition and subtraction problems. We round to the least number of decimals. So this is 2 decimals, 1, 4, and 2. What do we round to? 1. So 10206.5. So here we have 2 decimals. Here we have 3. We round to the least number of decimals, and we get 42.36. Okay. All right. So that's all with that math part. We're going to do dimensional analysis, finish that up, and starting tomorrow we actually do chemistry. So what we did in like a week last year, you're going to do, we did in a day. Right here, this is American system stuff. This is just to help you with today's problems. Do not memorize them, okay? What I do need you to memorize are your metric common prefixes. There are a lot more than this, but these are the ones that will be most useful to you. So just start learning them. No big fat rush. Definitely by the first test, okay? All right, so now let's start doing some dimensional analysis. I'm just getting different types, a single, a double unit, and then a cubic unit, one of each just for practice. So looking at this, again, there's going to be, I need new sheets here. These are all falling out. There are going to be different conversions you might want to use, and whatever we use is fine, okay, because there's more than one way to skin a cat. So a pencil is 7 inches long. What is the length in centimeters? So always start with your given. For today and for your homework tonight, just use what's in your given, okay? Don't worry about the conversion factors. Don't worry if it's American, going to use the sig figs in your given. So we're at that many inches long. I need to convert to centimeters, so I'm going to use dimensional analysis, and how am I going to set this up? Put 2.54 centimeters on top and 1 inch on the bottom. Inches cancel, and now I'm in centimeters, and that is it. So to 3 sig figs, what is my answer? We got to get the right answer for our videos here. 0.8. Bam. We good? Okay. The speed limit on many highways is 55 miles per hour. This is a double unit. When we have per, you set it up where it's miles per hour. The per is that division. Okay? So what would be the number in kilometers per hour? So we're going to leave the hour alone. We're just going to change those miles to kilometers. Do I have any runners who know this conversion? 1 mile is 1.6 kilometers. So where do I put miles? 1 mile on the bottom, 1.6 kilometers. My miles cancel. And to 2 sigfigs, based on the given, how many kilometers per hour am I dealing with? 88 kilometers per hour. Okay? Okay. A Japanese car is advertised as having a gas mileage of 15 kilometers per liter. Convert this to miles per gallon. So yeah, in America we have miles per gallon. So I don't know if that's a good mileage or not. 15 doesn't sound like very good. So let's see. Let's see what we really get and see if it's a car we want to buy. So we have 15 kilometers per liter. All right. The difference between this problem and the previous one is not only do we have to change kilometers to miles, we also have to change liters per gallon. The beauty about dimensional analysis is we can do either. We don't have to pick one or the other to go first. We can do either first. What do you want to convert first? The kilometers to miles, right? So now, this time, the mile is going to go on top, and our kilometer needs to go on the bottom so we can cancel. So 1.6 kilometers. So right now, if I were to stop the problem, what would my units be? Miles per liter. Well, still not quite what we want. Is there a conversion that we can use? We might have to do 2 steps here. Okay, right. So 1 liter is how many quarts? 1.06 quarts. So my liters cancel. And again, see how they're not right next to each other? You can do that. They still cancel. And then how many quarts in a gallon? 4 quarts in 1 gallon. So that's it. So what is my, I'm sorry, I can't hear you. 35. Is that good? Yeah, that's pretty good. It's better than my Jeep. My Jeep gets like half that, if I'm lucky. Okay? All right, we're almost done. We'll give you some time to work on your homework. You guys are awfully quiet. I couldn't get first period to be quiet. All right, no, they're actually fine. I'm just exaggerating. Okay, this is going to be a cubic one, just to give you some practice on that, because you need to know how to do cubic stuff. The latest model Corvette has an engine with a displacement of 6.2 liters. Well, we don't measure, well, actually we do. I have a 6-liter engine, and yeah, so I was going to say we don't use that, but this problem is requesting that we get it to cubic centimeters. So there is a measurement out there that is a translation between what we usually know as a length, which is then multiplied to be a volume, a cubic volume, to a volume of a liquid. Does anyone remember what that is? Naira? Exactly. 1 cubic centimeter, better known as cc, is equal to 1 mil. So when you watch TV and they're like, he needs 5 cc stat on those hospital shows, that's 5 mils. So cc stands for cubic centimeter. And if you were to make a little box that was centimeters on all sides, you could put 1 mil in it. Okay? All right. So that's our goal. This is, in order to get to that cubic length from a volume, we have to get to this point. So what would be the first smart conversion to do to get there? Let's get to milliliters. So for every 1 liter I have 1,000 mils. Okay. We're in mils now. So now what can I say? 1 mil is 1 centimeter cubed. So the mils cancel and the liters cancel. So right now I'm in centimeters cubed, but we don't want centimeters cubed. What do we want? Okay, so you have suggestions for us? Okay, sort of, close. Very close. Right, exactly. Well, I didn't know if you were cubing the number. You got to cube the number, not just, okay, cool. So she got it. So here we have, let me just write it like this first. So this is the equivalency that we know, right? There's that many centimeters per inch. But that's not cancelable. So we have to cube this. If we cube this, you cube the unit and the number. We cube the unit and the number. So what is, just so I can have it on the video, what is 2.54 cubed? You don't have to show this work. You can just put it in your calculator when you're doing your own stuff. But 16.387 cubic centimeters is what this number is, okay? So go ahead to 3 sigfigs. Tell me how many cubic inches we have. 178? 378. Oh my God. I keep making mistakes. 378 cubic inches. And that is the answer. Okay? All right, last problem of the day I like a lot because it's taking a very simple density problem, dimensional analysis density problem, which you might have done in pre-AP or regular chem really easily. And it's adding a smidge of a twist. And that's the main difference between this class and the class you had before. That's why it was really crucial for you to have that first year base, because now I'm just taking that base and I'm adding twists. Okay? So looking at this, we have a bottle of sulfuric acid. Okay. Does anybody remember? Oh, no. Oh, we're going to ignore that. It's the warm body count. I already did it. Okay, so does anybody remember the formula for sulfuric acid? Just because. You don't need it for this problem, but nice. H2SO4. So we have a bottle of sulfuric acid. It says that the density of all the liquid in this bottle, the density is 1.84 grams per mil. But if you look closely on the label, this is only 95% pure. The question is, how many mils of this, or liters, whichever we get, what volume of this do I need to pull out 100 grams of H2SO4? So this is taking some thought here. If it were 100% pure, it would be a super easy problem. I'd just take 100 grams, multiply it by 1 mil over 1.8 grams, and I'd have my mils. But it's not pure. So any ideas? Naira. What would I use that against, though? If you're setting up a proportion, what would the other side of the proportion be? The density. So you can do it this way. Well, let me do it the way that's in my head first, and then we can set up a proportion. I know this is 95% pure. So only 95% of this gram per mil is actually sulfuric acid. How do I find 95% of something? Multiply by 0.95. So 1.84 times 0.95 will give me how many grams per mil I actually have, which is what? 1.748 grams per mil is actually the amount that I have. Okay? So now I can take this and just do my dimensional analysis, starting with what I'm looking for. I'm looking for grams of H2SO4. How can I use this density to get me an actual volume? It's a double unit. What does this actually mean when we're doing dimensional analysis? Right. It means 1.748 grams over 1 mil. But we're not going to put it in this way. What are we going to do? We're going to flip it. For every 1 mil, it has a density of this, so there's that many grams for every 1 mil. Do you see how now grams cancel? And what do I have? Mils. Isn't that answering the question? Yeah. So to just this should really be, we'll put a dot here pretending this is 3 sig figs. To 3 sig figs, what do we get? 57.2? I need 57.2 mils of this stuff to actually get that number of grams. And so going back to Naira, because I think a lot of you think in proportions, I think she was saying 95 to 100 is the same as x to 1.84. Was that what you were saying? How to set it up originally? Which is the exact same thing as doing what I just did here, right? So whichever way you want to do it, this x would be that number. So I really don't care which way you set it up. So the first thing we did was find, okay, it's 95% pure, how much was actually there? And then we went ahead and just did dimensional analysis to see how many mils we need. Okay, any questions? All right, that is all. Go ahead and start your homework 1A. It's due tomorrow. Some of you are already done with it. Oh, while I'm thinking about it, homework 1A, the very first problem is you've got like something over something plus, it's a sig fig problem. It looks like this, okay? So in this one, you have to do multiple roundings. So you do each division, and when you divide, what do you round to? Sig figs. Right, so let's say this was 2.5 after the division, 2 sig figs. Let's say this one you divided and you had to do 3 sig figs, and this one you divided and you got that. You do the rounding individually first, and then you now add, and what do we round to when we add? Decimal places. So we have 1 decimal place, 2, and here we have none. You would round to no decimal places. Now, this is not the answers in the problem. I just made all that up, so you still have to do the problem. All right, I'm done talking. Work on your homework. Come talk to me if you have questions.